So, okay, we started recording. So, hi all, thank you for coming. I'm very happy to have Silvain Rideau from the University of Paris. Is that the name?
Yeah, it is the name.
The name, yeah, because
joking.
I'm just saying. He's part of the researchers on the big project we have for in our logic team in Costa Rica. So he was supposed to come to Costa Rica on May, but unfortunately, because of everything that happened, he couldn't make it. So he kindly offered to give a talk virtually. So yeah, he's gonna talk about asymptotic imaginaries in FP, well, in all that thing. And so yeah, thank you. You can start.
All right, thanks a lot for the invitation. As you can guess, I would much rather have been in Costa Rica last month, but hopefully I will get to come at some point. And so this is just a small delay. Okay, so as you can see, today I want to talk about this horrendous structure. No, I can't. Okay, this doesn't work the way I want it to work. Anyway, so it's a valued field with an operator. So I'll get to what this thing is later. So this is a joint work with Martin Hills, and well, that's all I have to say about it for now. So let's start with what valued fields are. So a variation on a field is essentially a more general thing, a more general version of a metric on a field. So essentially what you have, so you want a metric that's actually compatible with the operation of the field. So you want a group morphism from the multiplicative part of the field to some ordered abelian group, which usually when it's a metric, the ordered abelian group would be the positive reals with the multiplication. But in our case, we allow any ordered abelian group you want. And we require a stronger version of the triangle inequality. So we require, so it's written in a very weird way because valuation theorists are weird people. But if you, for historical reasons in valuation theory, the order is the other way around from what you expect it to be. And so what you should really think is that what I've written is distance is smaller than the maximum of the distances, which is a stronger version of the triangular inequality. But since the order is in the wrong direction, we write it this way. But really, it's just that. So so it's a metric with particular properties. In particular, you can show amusing things with metrics like that. You can show that every triangle is isosceles. So that's kind of fun. But that's not why they're interesting, as we'll see soon. Just for notation purpose, I'm kind of cheating in my notation because I told you that V was defined on the multiplicative group, but of course you also want to have a valuation for 0, and usually we define it to be infinity, which is bigger than everyone, which usually would be the other way around. Of course, you define V of 0 to be 0, which is smaller than everyone. But once again, we're backwards. Okay, good. Then some notation. So one reason why this strong triangular inequality is interesting is that actually the unit ball becomes a ring. So that's amusing. And this ring we call O. And not only is it a ring, so well, it's a ring, but it's also a local ring. So it has a unique maximal ideal, and the maximal ideal happens to be the open ball. The open unit ball. And okay. And so what do you want? Oh, yes. And well, whenever you have a local ring, the thing you want to do is look at the residue field. Okay, so this is going to be an important element of an important part of our structure, the residue field. And so before we move on, maybe I should give you examples. So you know valued fields. You've seen them in your life. The typical example, well, there are two typical examples. I'm just going to give one of the typical examples, at least in writing, because it's the one that's the most relevant to what we're going to talk about. If you take the ring of polynomials, well, I take the field of rational fractions, really. So you take the fraction field of that. So you take rational fractions, and you can count the degree or the pole at 0, and that gives you a valuation. So poles are counted in negative, and degree and roots are counted in positive, of course. And if you complete that thing, you get what's called the field of Laurent series, which is formal power series in T. So it's the fraction field of the formal power series, and you can describe them just as power series that might start at a negative degree. Okay, and the most general construction is actually called the Hahn series field, which given any field little k and any ordered abelian group big gamma, you can build out of this a valued field, essentially by considering that you're looking at formal power series where the degree is given by gamma. Okay, so you have to be a little careful what that means. There are conditions on things being well ordered and stuff like that, but essentially it's power series where the degree of the coefficients is given by gamma. In particular, the Laurent series is exactly the Hahn series field with a value group Z. Okay, so these are the kind of objects we're going to look at. And so in K, in the Hahn series field, essentially the valuation is also given by roots, well, generalized versions, well, formal versions of roots and poles. Okay, good. So these are valued fields. But as you probably noticed, this is a talk about model theory. So what we want to study is the model theory of these objects. But we want to study in particular one question about these objects. And that question is the following. So if I take M, a structure, and I look at a family of definable sets, so I take a set in the product, but really what you can think of it as really just you have well, now you have y here, which way? Yes, y here, z here, and then you have your blob here, which is x, and what we're going to do is to look at the fibers of this thing in y. Okay, so I drew outside of the PDF. It seems okay. I'll try to be careful. So this is what this is. Oh, maybe I can pull it back. No, I can't. Okay. Oh, I can. So this is what the kind of things we want to look at. Okay, so what we wish to understand is the set of fibers. So we want to understand the set of possible sets that can appear in this family. So this is a natural question in geometry. Whenever you have a family of things, you want to classify which objects appear in the family. Okay. Another way of seeing that question is that you can actually define a definable equivalence relation on Y, which is I have the same fiber. Okay. So the equivalence relation is just Y1 and Y2 are equivalent if well, they have the same z's such that the pairs are in X. And this gives you an equivalence relation on Y, and so you can look at this quotient Y mod E. So it's not a definable object per se, because we have a definable set and we quotient it by a definable equivalence relation, so we get something new. And what we would like to do is understand what this new thing looks like. Because, well, I don't know how much. So I see there are a lot of people I know and that very much know all of that, but I'm still going to say it.
Wait, I do have a question.
Yes.
Is it for all C?
For all, yes. What did I not write?
isn't it? Oh, okay. No, I mean, is it a fiber you want, or is it?
Yes, it's exactly the fiber.
Okay. Oh.
I just wrote the fibers are the same.
Yeah. Okay. Yeah. Thank you.
Yep. So you have a follow here. Yes. So as you possibly know, or not, one thing that model theorists love to do is to describe the objects, because the finer the descriptions we have, the finer the description we have, the easiest it is then to why is it not full screen? Oh, come on, stupid. Okay. Okay, that works. Yes, the finer descriptions you have, then the better you'll be able to say things about the subjects. And so usually what we like in model theory is to actually describe exactly what these sets look like, so that then we can do things with them. So that's what I mean by describe, is to give some kind of characterization of what these sets look like, ideally in terms of definable sets, because these are those that we understand much better. And so the ideal thing we want is that we want to find a definable function such that this quotient essentially looks like the image of f. So what do I mean by that? We want to find a definable function such that the equivalence relation we have here is exactly the fiber equivalence relation for f. Okay, so two things are equivalent if and only if they have the same image. And of course, if you have something like that, then you have an embedding of the quotient into a definable set. And so now the embedding, this quotient, which is something that we couldn't quite talk about, becomes a definable set, and we're quite happy about it. So this is a situation that we like. And so whenever f exists, we say, well, so whenever f exists for any possible choice of x, we say that C eliminates imaginaries. And as we'll see, actually what we do often is, well, in the examples I'm going to talk about, we don't actually have elimination of imaginaries, but I'll talk some more about that afterwards. So this is the main question we want to answer about these valued fields, is can we do that very thing? And so now let me talk quickly about the structure I want to do that thing in. Okay, so this thing here is the field I want to look at. So it's the Hahn series. Well, it's the Laurent series over FP, and then you take the algebraic closure of it. So it's some formal object which is an algebraically closed valued field. Then I have the valuation on it, and then I add a name for the Frobenius automorphism. So actually adding a name for the Frobenius automorphism does nothing at all, because so the valuation here is the t-adic valuation, the one we've been looking at, that I explained in the example. So yes, so in that case, adding the Frobenius does nothing, because the Frobenius map is just x goes to xp, and so it's definable in the ring language. So actually, this structure we want to talk about is just a definable extension of the structure where we only have the valuation and the ring structure, of course. So ACVFP is the acronym for algebraically closed valued field of characteristic P and residue characteristic P. And so that thing here is an expansion of it. And so the first question, so if we remember the previous slide, the first question I want to answer is, do we have elimination of imaginaries in this structure? And as I told you, the answer is no. There are a number of quotients that we can't eliminate. So in that case, there really are two options. Either we say, it doesn't eliminate imaginaries, let's go have a beer and forget about this problem and never talk about it again. Or we could say, well, okay, it doesn't eliminate imaginaries, but we know what quotients are the obstruction. So maybe let's just add these quotients and see if they're sufficient to describe everything. So this is exactly what we're going to do. So essentially, the obstructions come from the value group and the residue field, because you can show that they cannot be encoded in the field itself. It's not very hard. There are obvious cardinality issues. You have models where the field is much, much bigger than the residue field and the value group. There's no way you can eliminate imaginaries in the field alone. So you can't do that. And actually, if you start looking at things, you have higher dimension problems that also start to arise. And so you need higher dimension of these things, a higher dimension versions of these things. So that's what I'm going to define now. So the first quotient I want to consider is that quotient. It seems completely horrible, but it's not that horrible. So what it is, it's I take a basis of k to the n as a k vector space. And then instead of just considering it as a basis of k to the n as a k vector space, I consider the O module generated by this thing. So it's not a vector space. It's not a subvector space because we only multiply by things of positive valuation, but it's what's called a free rank n submodule of Kn. So I mean, as modules go, it looks like a vector space. And then if we have one thing like that, any two bases generate the same module if and only if they're conjugated by GLNO. This is the completely usual thing. So this object we're looking at is a moduli space of submodules, of very specific submodules. And the other set we want to look at is that, so maybe the first thing I should say is that in dimension 1, this is exactly the value group. You can check, it's isomorphic to the value. And so now I need something that looks like the residue field. And so that's going to be the thing I'm going to describe now. So now we also need, whenever I choose a lattice, so an element of SL, I want to look at its reduction mod the maximal ideal. So this is also, well, it's not that complicated an object. Actually, what it ends up being is a vector space over the residue field. So it's a residual object that's around. And actually, you can show that, well, these things are clearly quotients in my structure, and so they have to be around. And so, and the amazing theorem is that this is the only thing there is about. So you could be a bit disappointed because I'm telling you, well, you don't eliminate imaginaries, but if you add these horrible things, you do. But really, they're not that horrible. They're they have a very algebraic and geometric nature, and so you're actually quite happy to know that these are the only things around because you know what they look like, and so you can try to do things with them. And so it's actually very helpful to know that this is all that there is insofar as quotients are concerned. Moreover, you can actually show that these are necessary. Okay, so if you remove cofinally many of the SNs and the TNs, you can't have elimination of imaginaries. So really, you can't do much. You can't not work with them. If you want to seriously do model theory of valid fields, you have to work with them, which I guess is a good reason to consider. Okay, good. So of course, as I told you, we are looking at a definable expansion of algebraically closed fields with in positive characteristic. And so the imaginaries of these things are completely understood because, well, they're just these imaginaries. Of course, we're looking at the definable expansion, so the imaginaries don't change. Okay, good. So we've understood this structure, but the question I want to understand is what happens as p goes to infinity, because well, often. So here, really, what the theorem here tells you what happens for fixed p. But if you want to understand asymptotic behavior, so if you want to understand how things vary as p varies, one interesting thing to do is to understand the asymptotic behavior as p when p is very, very large. And as we well know, model theory has a very nice way of doing that because we can consider ultra products. And so the first remark is that if we forget about this Frobenius business, then we're really just looking at an algebraically closed field of equicharacteristic 0. Okay, so if we take FPRs with the valuation and we take the an ultra product as p tends to infinity, then what we're going to get is just an algebraically closed field of characteristic 0 and residue characteristic 0. And these we understand because Haskell-Reshevsky-McPherson theorem also applies to this structure. There was no restriction on the characteristic. So this we understand. But you might have seen that I've cheated because I've forgotten about my Frobenius thing, which is kind of the point. What we want to understand is what happens with the Frobenius as P grows, because the rest we understand very well already, because, well, we only get a field, which is not anything new. And so what we really wanted to understand is this thing. Okay, we want to understand the ultra product where we also have the Frobenius. And so what we get in the end is a field with a valuation and an automorphism, because the Frobenius is an automorphism for OP, and so in the ultra product it also is. So it's an automorphism, but it's actually new structure because it's not given by a polynomial now. It's given by some weird thing. I mean, it's a limit object, and now it's actually new structure. So this is the structure we want to consider. So there are a number of things we know about it. Let me check the time. There are a number of things we know about it. And first of all, I can tell you, well, as this is just how ultra products work. The residue field is the ultra product of residue fields. Okay, so the residue field of this thing is Fp, and I have the trace of the Frobenius on it. So the residue field also comes with an automorphism, and it's just an ultra product of algebraically closed fields of characteristic P with the Frobenius. Well, just between quotation marks, because as we'll see, this is a complicated object. The value group is also pretty simple. So the value group of each of these fields is Q. And the Frobenius acts as P on it. So it acts as multiplication by P on Q. And so, so the value group is just a group gamma with an automorphism sigma, which is obtained as an ultra product of this structure as an ordered abelian group with an automorphism. Good. But that doesn't quite tell us what this field is. Because it could be a very complicated valued field. But there is an important theorem. Well, there is an important concept in the model theory of valued fields, which is that most of the time, things come from the residue field and the value group. And in the particular case we're interested in, this is made explicit by a theorem of Hahn that says that the structure we are interested in actually is elementarily equivalent to a Hahn series field, where so little k is the same little k, gamma is the same gamma, and the automorphism can be obtained can be computed very easily from the automorphism on little k and the automorphism on gamma. So it's just that you move things around. So as I told you, elements of the Hahn series field look like formal power series with a degree in the value group, and you just move the coefficient, move the exponent, and that's your automorphism. So the structures we're really trying to understand are really Hahn series fields built out of this field and that group. Okay, good. Well, that's so at least we understand what the structure looks like up to elementary equivalence. The value group is actually, the theory is complete. Okay, so it's I gave a name to all of this, but essentially the only thing I want to say is that it's a complete theory. We have no axiomatization for it, so we know a lot of things about it. Actually, it's I forgot to say, so it might appear later. So it's a non-minimal expansion of Q as an ordered group, and so okay, it's essentially what you've given yourself is you've given yourself multiplication by an infinitesimal element. Good. The residue field is a much more complicated object. So this is a very hard theorem. So much so that not everyone agrees it's a theorem. But for today, we'll just make do and pretend it's a theorem. Actually, I don't use the theorem in what I'm going to tell you later. It's just to explain, to characterize what. Well, actually, I do use it. Okay, so scrap that. I do use it later. but yeah, so what is this theory? So we actually know what is the theory of this thing. So it's this theory ACFA 0. So what it is it's the model completion of fields with an automorphism. So essentially what this theorem says is that when you take the ultra product of the FP ℝg with the Frobenius, what you get is the generic behavior of a field with an automorphism. Okay, so it's the most closed field you could possibly get. So this is not a complete theory, but we exactly know what the completions are, and they are given by the algebraic closure of the base of the prime field. Actually, the action of the automorphism on it, but whatever. So this is also a pretty well understood theory, but up to, well, ACFA 0 is a pretty well understood theory. The fact that we're actually looking at that theory is a very hard theory. But anyway, so this gives a reasonable picture, at least insofar as the theory is concerned, of the field the structures we're trying to look at. So okay, so now what questions do we want to answer? So as always, when we look at the structure in model theory, the first question we want to answer is what do definable sets look like? So for now, I told you my main question was what do quotients look like? But I mean, the first question we should answer is what definable sets look like. So they're a bit complicated because the residue field is a bit complicated. So this theory here does not eliminate quantifiers. So there are quantifiers around that we have to deal with. And so the best result we can hope for is the following. So we introduce a new sort that I'm going to, well, a new quotient that I'm going to call RV. If you think about it for a minute, you'll see that RV is actually T1 that I introduced earlier. So actually, we've already seen this RV, but it was named otherwise. Okay, so what it is, it's the quotient of the multiplicative group by the things that are close to the unit. So, okay. And then what I'm going to do is work in a language where I have both a sort for the field and a sort for RV. I'm not going to actually describe in detail the structure you put, but you can think that what we're going to do is put the ring structure on both sets. So you have to think for a minute what the ring structure on RV is, because it obviously has a multiplication, because this is a quotient of a multiplicative group by a multiplicative subgroup. But the addition is a bit more annoying. But remember, RV is T1, so it's a collection of one-dimensional k-vector spaces, and the addition is actually the addition of the vector spaces. Okay, so you have a multiplication and addition on both, and you have a map that I'm going to call little RV. I should probably have said so. You have a map called little RV that goes from K into RV, which is just the canonical quotient. Okay, so so this is the language I'm going to work with, and well, I should probably have given the theory I'm looking at a name earlier, but now I'm giving it a name. So I'm going to call VFA 0 the common theory of all these ultra products I'm looking at. And I'm going to consider it in the language RV because why not? Okay, so it's the common theory of all these ultra products, and you can actually axiomatize it. This is essentially what the previous slide was about. You can axiomatize it by saying a bunch of things. So it looks like a Hahn series field, which is usually called being sigma Hanselian. And the value group is this complete theory I told you about. And the residue field is that other not complete theory I told you about. Okay, so this is the theory VFA 0 that we're considering. And we essentially know what definable sets look like. So as I told you, we can't quite eliminate quantifiers because there are quantifiers on the residue field that can't be eliminated. So we can give a more precise theorem than what I've given here. Here I'm trying to pretend that the only thing that we can do is eliminate quantifiers on the sort K. So I'm pretending that you have arbitrary quantifiers on the sort RV. This is not true. The only quantifiers you have on the sort RV are actually existential quantifiers. And you can actually show that you only need algebraic existential quantifiers. So there are a few who there are quantifiers around, but most of them, I mean, not much. Okay, and so that kind of solves the question of what definable sets look like. And so, as I told you, what I want to tell you about is what do quotients look like. And so the theorem of Martin and I is that this theory VFA0 eliminates imaginaries up to these sorts that we already needed anyway because of the valuation that is underneath. So remember, whenever we have a valuation, we have quotients that appear, which are these SNs and these TNs. And so G is just K and all these SNs and these TNs, and that's essentially the best result we can hope for. And this is the result we get, so I guess this is not too bad. Okay, so now, if I'm not completely mistaken, I have around 20 minutes more. And so what I would like to explain a bit is how do we prove that here? So things are going to get a bit more technical. But hopefully they'll stay comprehensible, and don't hesitate to ask if there are things I forget to define or things like that, or if anything makes no sense. Okay, so so now what we want to do is to explain that theorem. Well, what I want to do is to explain at least ingredients of the proof of that theorem. And so the first ingredient is the following. So it's a result of mine that well, it's a technical tool of mine that I developed to understand a somewhat similar case, where instead of which was a valued field with a derivative instead of a valued field with an automorphism, but essentially they were the same kind of questions, which is that you have so you want to understand what definable quotients look like, and essentially the first step is to try to try to find a lot of definable types around, because we like definable types. So so what's the setting? You take an enrichment of the theory ACVF, and you take a model of that theory, and you take a definable set in that structure. So you can kind of forget about the strict pro thing. It's just that actually, if I'm completely honest with you, in the proof I will need an infinitary version of the argument of what I'm explaining to you. And so this strict pro thing is to allow for the infinitary part of what I want to do. Essentially, I allow definable sets in infinitely many variables, being careful that I don't end up with something I can't control. Good. So so you can forget the strict pro and just consider that X is definable. And so now what we want to do is to find a type in the reduct in ACVF, which is generic in X. So in a sense, oh yes. So, but before we do that, I have to explain what I mean by generic. So generic maybe is not exactly the right term to use, because generic has a lot of very precise meanings in various fields, among them model theory. So maybe what I really want to find is a canonical type. So maybe that's a better type. And so how will I detect canonicity? I will detect canonicity by seeing that the thing doesn't move too much when I play around with automorphisms. Okay, so I want to consider the following group that I'm going to call A. This is a in Gothic. And so it's the set of automorphisms that don't move my X. Okay, and then I'm going to look at the set of points that are fixed by this automorphism group. So if that feels a bit like Galois theory, it's because it is Galois theory in a very precise sense, but which I'm not going to get into. But yeah, so what we want to do is we have an X, and then we look at everything that fixed when X doesn't move. And I'm not going to get into the details, but proving elimination of imaginaries is essentially equivalent to proving that X is definable over big E. Good. Actually, I've lied to you. Okay, well, the real E I wanted to define for the rest of the slides to make sense is the thing that have finite orbits under the action of A, and not those that are fixed. But we'll ignore that little problem. Okay, good. So I have my set E, which essentially are all the points that don't move when X is fixed globally. So it's kind of the canonical points related to X. And yes, so just for notation, I will denote by type index 0 the type in the underlying ACVF product. So this is ACVF redux. So this is just a type in the language of valued fields. So it just uses the ring structure and the valuation. Okay, and the interesting proposition is the following, is that assuming some nice behavior of the residue field and the value group, we can always find a type which is definable over E and which lives inside X, which is consistent with X. So remember, X is defined in an enrichment, so a priori the type doesn't force its realizations to live in X, but it's just consistent with X. So it has one realization that lives in X. Maybe I should quickly say what is this definability business. So the thing is that most types, so remember types are collections of formulas, and so most types are very infinitary objects. They're horrendously complicated because they have as much information as their parameter set. So in that case, the type of A over M is contains a lot of information because M is very big, and so this is a very infinitary and big object, and it's not very tractable. So what we prefer to look at are definable types, which are types where you can actually say when a formula is in the type. So I'm not going to give the precise definition, but essentially these are types which are characterized by a finitary amount of data, which is much better so that you can speak about them. So in particular, in that case, the finitary amount of data is just over big E, which is the canonical set that comes from X. So in that sense, this type here doesn't move when X doesn't move. Good. So for those of you who know a bit of algebraic geometry, I really think of this proposition as a form of Zariski closure. So usually, if you're in a field, you have a set in a field, you can look at the Zariski closure of that set, you get a variety, and well, depending on what your definition of a variety is, you get a variety, and this variety kind of encodes the generic behavior of your set as a field, inside the field. And in a way, this is exactly the same thing, except because life is harder in a valued field, you don't actually get a set, you only get a type. But essentially, it's the same thing. In a way, if we didn't have the valuation, so if you have a set inside a field, you can take the Zariski closure, and then you can look at the generic points of the Zariski closure, and these are exactly going to be the types we're looking at now, except now we do the same thing, but with evaluation. So it's a bit more complicated. Okay, good. So the first ingredient I've been trying to describe is that whenever we have a set, we can find generic valuational behavior in that set. Good. A little remark. Why can we apply this result to VFA0? Well, the value group is stably embedded and non-minimal, so it eliminates exist infinity. And little k is stably embedded in a pure model of ACFA0, and we know that ACFA0 eliminates exist infinity. So actually, without the 0, it also eliminates exist infinity. The 0 is not important. So these two theories are known to have the right properties, and so this proposition can be applied in my theory. So if I start with my set X, I can find generic valuational behavior in it. But as I explained when I was explaining the statement, one core issue is that this type here in M is not a complete type, because it only talks about the reduct to ACVF. So now the second natural question is, what are its completions? Okay, I have found the variational data that's consistent with MLX. And so now the question is, what are the possible completions of this thing? And so, so this is what we're going to look at now. So I have my model of the FA0. I have a bunch of geometric points in it. And so G stands for geometric. And oh, this should be an M. I'm sorry. I don't know where there is an A in there. And we have a tuple in some elementary extension whose type we're going to look at. But we have one thing we have to do first, which is that, remember I told you that there is some infinitary business going on, which is that we have an automorphism. And so the real things we want to look at are valuational data on the prolongation of that element. And so this is the prolongation. So it's the set of all of the image of that point under the automorphism. Okay, good. And if we rephrase Ashkin's quantifier elimination result, we can rewrite it in this way. So we can rewrite it by saying that to know the type of A over K, the only thing I need to know is the valuational type of the prolongation and the type of something that generates the RV. Okay, so I need to know the type of the prolongation and the type of some rho A that generates the RV of the field generated by nabla A. Okay. Good. So this is what the quantifier elimination tells you. So if you have chosen an A whose type 0 you already know, the only thing we need to explain is what does this part look like. And actually, what we're going to do is completely ignore this part. Well, we're not really completely ignoring it, but we're going to cheat by saying this part essentially is what it is, and we can't say much more about it. Because really, we can't say much more about it because this structure, the RV here is very complicated, and so there's not much we can say about it. So, so what we're going to try to do is to ignore what's going on here and try to still say something about possible completions of this type. Okay, so this is what we're going to do. Let's assume that this type here is definable as we've done earlier. And so I pretend that the following is true. So I'll give you the notations afterwards. But essentially, sorry, I won't. That's I want the corollary. So the type is complicated, but so it doesn't move too much if we fix a big set. Okay, so that seems a bit disappointing, somewhat disappointing result, but as I'm going to show afterwards, it's already a good result because this set is big, but so its class size, it's the same size as the model. Actually, K should be M everywhere. I'm really sorry, I need to in the middle, and K should be M everywhere. Anyway, or K is equal to M. Okay, good. So any type whose underlying valuational type is definable actually is invariant over some big set, which is built out of, well, not just RV, but also certain things that come from the residue field. So what are these things? Well, they're called the linear part over E, and they're exactly these vector spaces that come from the lattices in E. And so DE is the union of E, RV, and all these linear things that live over the residue field. And so then so the the technical tool that allows us to prove this invariance property is the following. It's that, well, the row A we have here, the generating set inside RV, can be chosen to be very invariant. Okay, so we can find a row that's invariant and that generates. The problem is that it doesn't quite live inside RV, it lives inside this bigger thing, which is why in the end we only get invariance over the bigger thing. So yes, as I told you, this is actually a nice result, because remember what we were trying to do. We started with an X, we found generic valuational behavior in it, and then so maybe I should start drawing things if I can. So we started with an X, that was our X, and then we found some type P0, which was generic valuational behavior that actually was very close to X, and which was fixed when X was fixed. And then we took any realization of it, and we found a type P here, which does not move under the action of that group. Okay, so the action of that group fixes it. It sends it to itself. So now, if we think about what we've done, X now, when we act with this group, X is not going to move either. Actually, I'm lying when I say that. This would be the case if X happened to be the equivalence class of some equivalence relation defined over no parameter, but it's not very hard to reduce to that case, because as we saw, what we really care about are equivalence relations for things defined over the empty set. So if X actually were an equivalence relation, since we fix a point in it, we actually fix X. So what we've shown is that X does not move when we fix this set. And so then some magic shows that essentially, if you want to understand the imaginary associated to X, what you have to do is understand the imaginaries in that structure. Okay, so essentially, all these complicated things have reduced the question of elimination of imaginaries to elimination of imaginaries in that structure. Good. And so the last ingredient is what can we say about this DE structure? So remember, DE is E, so it's a bunch of points, so that's really not a problem. It's RV and it's lin E. So lin E, as you remember, is a family of K vector spaces, but they also come with an automorphism. So the problem is that we started with an automorphism, but when we take a given lattice, there's no reason that the automorphism fix it. So actually what we have is not really an automorphism, it's a bunch of isomorphisms that send vector spaces to vector spaces. Actually, these structures are well understood. A theorem of Rorschowski, well, a theorem of Rorschowski almost, shows that this thing eliminates imaginaries. Okay, so that's for the first part. For the RV part, RV is a short exact sequence of modules. So yes, maybe I should have written that down at some point. So remember, RV, what was it? It was K star mod 1 plus n. And so there's a natural map to gamma, which is just K star mod O star. And the kernel of that thing is O star mod m star, 1 plus m star. So this is just little K star. Okay, so we have a short exact sequence. So this is RV. So RV is an extension of gamma by an enriched group, which is just the field. And these are also well understood. So there's a bunch, there are a number result on this, and for example, you can show that this structure eliminates imaginaries in the two second elements of the short exact sequence. So of course you need to have points for gamma because it's a quotient and it's there, but this is all you need. You don't need more than that. And then tweaking around this proof, you can actually extend it to DE. So remember, RV DE is the combination of lin E and RV plus points, which don't really matter. And actually the structure live independently enough that you can actually put the two results together and prove that this D structure eliminates imaginaries relative to itself plus gamma. And if you put everything together, you get that theorem, which was the theorem I told you about earlier. Okay, so what was the idea? We started with a set. We found generic valuational behavior in it. We completed that thing, possibly adding parameters from a set DE, and then we proved that D itself eliminated imaginaries, and voila. Okay, I'm done for today.
So, thank you so much, Silvain.
Thank you, Silvain. So I'm not sure if there are any questions. Please go ahead. Okay, I guess there are not a lot of questions.
I do have a question.
I have a question.
Although it's not
Dario tiene una.
completely related. Silvain, hi. I was just wondering, so you were working with an ultra product of algebraically closed valid fields, right? The only thing that you were changing was the characteristics. But do you know what happens when you consider the ultra product of QP? I mean, what I'm asking probably is, do you know if there is a successful elimination of imaginaries in QP and whether or not these techniques translate to the ultra products?
Yes, so this is all done in a paper of UDMI.
Okay.
So QP eliminates imaginaries, and the ultra product of QP eliminates imaginaries.
But you don't need to add any extra sorts.
You can actually get rid of some sorts because QP has a discrete valuation, and so the TNs are useless.
And does it? I mean, the elimination of imaginaries includes the elimination in the pseudo-finite field, which is going to be the residue field.
Yes. Well, actually, you need to add constants to take care of the residue field. But,
okay.
But so essentially, what you need is a constant to encode the Galois group, which is essentially what you already need in the residue field.
And you don't get any problem from the fact that there is not an IP, right?
No.
Okay.
So actually, I don't. Maybe you. I've been giving a bunch of talks. So this paper hopefully should appear one day. And in that paper, there are more things, which is why it's not appearing. And in particular, there is a somewhat general treatment of all Hahn fields,
okay.
which explains that you have a kind of Akrosh-Arshoff type situation.
Okay, thanks.
There is also a question in the chat.
Yes. Look at the question.
Okay, you can.
So actually, there are two questions here, so let's. Where is it? No, it's after. Maybe somewhere. Yes. So that result. So what I claimed here is that the residue field models ACFA, and so this is just Udi's result that says that if you take an ultra product of algebraically closed field with the Frobenius, what you get is a model of ACFA. So this is the generalization of the theorem of Ax that says that when you take an ultra product of finite fields, you get, well, a pseudo-finite field, obviously, but depending on the definition of pseudo-finite. So this in a way is a generalization of that first theorem, and it relies heavily on something called, so axis theorem relies heavily on something called the Langevin approximations, which explain how many points there are in a variety, how many FP points there are in a variety as P grow. And so what Udi proved is that you have a similar result called the twisted Langevin approximations that explains how many points there are in a difference variety over FP with the Frobenius as P grows. So it's varieties that can involve the automorphism. So it's solution of equation of difference equations. And from that result, that's an asymptotic result. It's not hard to see that this structure verifies the usual geometric axioms of ACFA. So, but another underlying thing is that it's very amusing that actually here I just stated that the residue field is ACFA, but actually the field itself also is ACFA. It's completely obvious because the field itself is an algebraically closed field with the Frobenius, and P tends to infinity, so it's ACFA. And so in the end, what we get is that this Hahn series field here, this Hahn series field, built out of an ACFA and some object, is actually itself an ACFA. And I don't know a proof of that fact that doesn't go through these theorems. Okay, so the fact that this is an ACFA, it's because it's elementary equivalent to an ACFA. But the fact that this is the thing on the left is an ACFA is a consequence of that very hard theorem. So possibly there is a proof that this thing is an ACFA, but I don't know it other than going through this theorem. I don't know if that answers, if this answers what you had in mind. But,
yes.
Okay, are there any more questions?
I do have a question.
Yes, go ahead.
In the Hahn series field, what does the valuation ring looks like?
It's exactly the series where you start at 0.
Oh yeah, the zero of the group.
So the valuation is the smallest gamma that appears in the series. So the valuation ring is the one that starts at 0 or above 0.
All right, thank you.
So yes, to be precise, so you don't look at all power series like that. You look at those where the support, which is the set of gammas where C gamma is not 0, is well ordered. So if you want the full definition.
And the coefficients do not matter.
No, yeah. So you arbitrary C gammas, but you restrict to those where the non-zero C gammas happen on a well-ordered set.
Mm-hmm.
So in particular, you always have a minimum, and that minimum is the valuation.
Okay. Any more questions? Well, if there are not any more questions, we can thank again Silvain for this wonderful talk. And
Merci. Thank you, Silvain. And thank you, everyone.
Thank you, everyone, for coming.
Rafa, perdón. Yeah. Hacemos la foto.
So yeah, maybe we can we can make a photo screen, just like to have a memory of this wonderful talk. So.
With our cats, if we can.
Yeah, my cat is just here. In fact,
I want the cats on the picture.
Yeah, my cat is so asleep. So.
Okay.
Ok, voy a hacerlo a la 1. Ah, bueno.
No, espérate.
Falta John, sí.
So everyone is ready.
If everyone wants to put their photo, I mean like video.
Sí. Todos caben en una sola. Entonces, a la 1, a las 2 y a las 3. Listo.
So, thank you again.
Thank you, Silvain.
Okay. Bye, everyone.
Luego.
Luego.
Hasta luego. Chao.
Chao.
Bueno.
Ok, la termino entonces.
Ah,
Hasta luego.
gracias, chao.
Con gusto.